we will see the solutions of set 3 questions. If the intrinsic carrier concentration of silicon at room temperature is 1.5 into 10 raised to the power 10, first we will write out this particular data. Then what will be the concentration of electron in the silicon semiconductor doped with pentavalent impurity, given that new Fermi energy level EF is 0.28 electron volt above the intrinsic Fermi energy level, and electron concentration is asked. This question is very simple, as we have a direct formula. And we also know that KT is equal to 25.9 milli electron volt at room temperature, but for simplicity we can also take 26 milli electron volt. Now N naught will be equal to 1.5 into 10 to the power 10 exponential 0.28 electron volt, which is provided in the question itself, divided by 0.026 electron volt. After using virtual calculator, I got the value to be around 4.75 into 10 to the power 4, which gives the electron concentration to be around 7.13 into 10 to the power 14 per centimeter cube. The data which is provided in this question is NC to be equal to 3.24 into 10 to the power 8 per centimeter cube. NV is provided to be equal to 10 to the power 6 per centimeter cube. As the semiconductor is kept at room temperature, we can assume temperature to be equal to 300 Kelvin. It is also given that intrinsic carrier concentration is equal to 1.27 into 10 to the power 7 per centimeter cube, and temperature is given to be equal to 400 Kelvin. We have the formula Ni is equal to Nc into Nv under root exponential Eg divided by 2 kT, and we have to find band gap energy at 400 Kelvin. We are provided effective density of states in conduction band and valence band, but at 300 Kelvin, and the band gap energy is asked at 400 Kelvin. And you also know that Nc is equal to 2 pi effective mass of electron into kT divided by h square raised to the power 3 by 2. So you see that effective density of states is proportional to temperature raised to the power 3 by 2, and same goes with Nv. So it means that Nc upon temperature raised to the power 3 by 2 is a constant. Now Nc at 300 Kelvin upon 300 raised to the power 3 by 2 is equal to Nc at 400 Kelvin divided by 400 raised to the power 3 by 2. It implies that Nc at 400 Kelvin is equal to Nc at 300 Kelvin multiplied by 400 divided by 300 raised to the power 3 by 2. Similarly, we can also write that effective density of states in the valence band at 400 Kelvin is equal to effective density of states in valence band at 300 Kelvin multiplied by 400 divided by 300 raised to the power 3 by 2. Now we simply have to put the values in this equation. Intrinsic carrier concentration is given to be 1.27 into 10 to the power 7, and we have to put the value of Nv and Nc at 400 Kelvin only. We can see that Nc at 400 Kelvin is equal to Nc at 300 Kelvin, which is provided in the question to be equal to 3.24 into 10 to the power 8 multiplied by 4 by 3 raised to the power 3 by 2. Now we have to write Nv, which is Nv at 400 Kelvin will be equal to 10 to the power 6, which is Nv at 300 Kelvin multiplied by 4 divided by 3 raised to the power 3 by 2. After that we have exponential minus Eg divided by 2 into 26 into 4 divided by 3. We know that KT at room temperature is equal to 26 millielectron volt. So KT at 400 Kelvin will be equal to 26 divided by 300 multiplied by 400. We cancel out the zeros, giving us the value 26 into 4 divided by 3. Now only the calculations are left. After calculating with the virtual calculator, we get band gap energy to be equal to around 54 millielectron volt. This is the final answer. We have a direct formula for this question. Lambda in micrometer is equal to 1.24 divided by band gap energy, which should be in electron volt. So for the third question, we have lambda in micrometer to be equal to 1.24 divided by 1.1. It is good for you if you remember the band gap energy of silicon at room temperature, or otherwise you can find the value of band gap energy of silicon by this formula. But it will be very beneficial for you if you remember the value of band gap energy of silicon and germanium at room temperature and 0 Kelvin. So after calculating, we will get lambda to be equal to around 1.127 micrometer. And for the fourth question, what will be the cutoff wavelength for germanium at 400 Kelvin? Now here you have to use the formula. So the band gap energy of germanium at 400 Kelvin will be equal to 0.6958. Now we can use a formula. After calculating through virtual calculator, the value will come around 1.78 micrometer. Now we come to our last question. Consider a silicon sample at 300 Kelvin such that Nc is given to be equal to 2.8 into 10 raised to the power 19 and Nv is given 1.04 into 10 raised to the power 19. It is also given that Fermi energy is 0.26 electron volt below the conduction band and band gap energy Eg is given 1.12 electron volt. Now the question is asking free electron concentration. However, we actually have a simple formula which can give us the free electron concentration. We actually don't even need this and this value. After calculating through virtual calculator, the value comes out to be around 1.27 into 10 raised to the power 15 per centimeter cube. This is the final answer. Questions were easy. Second question was little bit lengthy but still manageable under the given time.